Hi everyone! Today we're going to start chapter 17, which is thermochemistry. So thermo means heat. Chemistry obviously means study of matter and the changes that matter undergoes, so chemical reactions. And so we're going to study the heat changes or transfers in a chemical reaction or in different processes. So thermochemistry is the study of energy changes that occur during chemical reactions and also in changes in state. So we know the typical definition of energy, which is more of a physics definition, is the capacity to do work. In chemistry, it's more the ability to produce heat. So in chemistry, we don't really think of work. We think of energy more in terms of heat. So energy is anything that is not matter but can cause a change in a chemical reaction. So things like light, like heat, like electricity, these don't have mass or volume, and so they're not matter, but yet they cause changes in a chemical reaction. So that's more of the chemistry definition. This is more of a physics definition of energy. So what is heat? Well, heat is the energy that is transferred from a warmer object to a cooler object due to a difference in temperature. For example, if I hold a very cold apple, because my hand is warmer than the apple, my hand will transfer energy to that apple. So the particles in my body are going to give off energy to the apple so that the particles in the apple start moving faster and the particles in my hand start moving slower until we reach the same temperature. But if I were to hold a cup of hot coffee, for example, the hot coffee is a higher temperature than my hand, and so the energy will transfer from the coffee to my hand, again, until we go to the same temperature. Energy is conserved, we know that. That's the first law of thermodynamics. It cannot be created or destroyed, but it can change from one form to another. So we have two main types of energy. We have kinetic energy, which has to do with motion, and kinetic energy is related to temperature. So the higher the temperature, the faster the motion of the particles. We also have potential energy, which we think of as stored energy. I don't like the word stored energy because it makes it sound like there's energy stored in bonds or something. That's actually not the case. Potential energy is energy due to the position of the particles, the kinds of particles, the size of the particles, and their position and arrangement. So I think of potential energy as positional energy, energy due to position. Kinetic energy is energy due to motion. So with kinetic energy, the faster moving particles have more kinetic energy. With potential energy, the farther the particles are, the more the potential energy, because particles are attracted to each other, and so the farther you need to keep them separated, the more potential energy, positional energy they would have. Potential energy can be converted into kinetic energy, and of course vice versa, kinetic can be converted to potential energy. So what are the units of energy? Well, the SI unit for energy is a joule. Capital J is the symbol for it. And a joule is a kilogram meter squared per second squared, or it's a Newton meter. You don't need to memorize this, but a Newton meter, so if you were to take a medium-sized apple, it weighs about a Newton. So if you were to move that apple 1 meter, so if I hold it up and move it up 1 meter, then I've exerted a joule of energy. A meter is about a yard. So if you were to take a medium-sized apple, move it up about a yard, you've exerted a joule of energy. So it's a pretty small unit of energy. In the United States, we usually use calorie, and in other countries as well, they use calories. A calorie, by definition, is the amount of energy required to raise 1 gram of water by 1 degree Celsius. A gram of water is a milliliter of water, is very, very small. And And you, if you were to take a gram of water, which is pretty small, and raise its temperature by just 1 degree Celsius or 1 Kelvin, a change in a degree Celsius and a change in 1 Kelvin are the same thing, then you've exerted a calorie of energy. So again, it's pretty small. It's not that significant. 1 calorie is equal to 4.186 joules. So 1 calorie is about 4 times as much energy as a joule. Now, if you look at any of your snacks, if you look at the nutrition labels and the snacks, if you have any handy right now, you'll see that the calories that you read there are always with a capitalized C. So a big calorie is what we call it, the ones with capital C's. Those are different from the little calories we just talked about. So notice that this is a small c. So 1 little calorie is the amount of energy that's needed to raise 1 gram of water by 1 Celsius, which is about 4 joules. A calorie that's on the food is 1,000 of those little calories. So 1 big calorie is the same as 1,000 little calories, which are the same thing as 1 kilocalorie. And so that would be about 4,000 joules. So let's think about this. An average person needs to eat about, 2,000 calories, big calories a day, right? That's the average. Obviously depends on your age, your body type, your activity type, your gender, all kinds of stuff. But the average, when they put the nutrition labels there, they'll say, oh, this is based on a 2,000 calorie diet. So the average person needs 2,000 calories, which means you need 2 million little calories, science calories, which is more than 8 million joules. So that tells you a joule is really, really small. You need more than 8 million joules every single day. So a joule is a very, very small unit of energy. This big calorie is usually only used in the United States. In other countries, they use kilocalories. So just that way we don't get confused. Do you mean the big calorie or the little calorie? But in science, we usually use little calories and kilocalories. A big calorie is 1,000 of those little calories. So how much is a joule? We said a joule is a very, very small amount of energy. And we already talked about if you had a medium-sized apple and you raise it up by 1 meter, then you've exerted a joule of energy, which is not that much. And a joule is about the energy that you need for 1 heartbeat. Think about how many times your heart beats in a minute. What is it, like 70 or something like that is the average? And how many minutes are in a day? And so, or an hour, and how many hours are in a day? So that's a lot, right? And that's just for your heart to beat. It's not even for, you being able to get up or talk or anything like that. So it's a pretty small amount of energy. If I light a little match, that's about 1,000 joules. So let me light a match for you. When the match burns, that's going to give you 1,000 joules. So again, that's not a lot of energy, and that's more than 1,000 joules. So a joule is a very, very, very small amount of energy. I'm gonna light, let's see, I have some Cheez-Its here. I'm gonna light a Cheez-It for you just to show you how much energy this is going to give off. You can try any little snack that you have. Can you see it? See how long this is going to last for. It's going for a while, right? So if you ever need to start a fire, you can use a Cheez-It or a Dorito or something like that. Well, still going. That's a lot of joules. That's a lot more fire than we had in our little match there. It's definitely more than 1,000 joules. And that's one little Cheez-It. So definitely need lots of energy every single day. We said more than 8 million joules every day. All right, so we need to be able to convert between these units. It's almost gone. Still going a little bit. Okay, so let's convert between these units here. So we have 782 joules, and we want to go to calories. So we're going to write what we have, like we've always done, 782 joules. Start a conversion factor. On the bottom, we're going to put joules. On top, we're going to put calories. And we know that 1 calorie is equivalent to 4.186 joules. So 1 calorie, 4.186. So we're going to do 782 divided by 4.186, which gives us 300. Oh, wait, that's not right. Sorry about that. So that is, with sig figs, 187 calories. Let's do the next one. 2,000 calories. We want to go to joules. So we're going to put calories on the bottom, joules on top. We know that 1 calorie is equal to 4.186 joules. So with sig figs, we need only 1 sig fig here, so that should be 8,000 joules. Next one, we have 650 calories. We want to go to kilojoules. So if you already know how to go to kilojoules right away, you're welcome to. For me, I like to do it in little steps, so I'm sure. So I'm going to go to joules first because I know 1 calorie is 4.186 joules. And then I'm going to say, put joules here, kilojoules, because these cancel. I'm at joules now, so I put joules on the bottom, kilojoules on top. 1 kilojoule is 1,000 joules. And that gives us 2.7 kilojoules. Let's do the last one here. We have 0.09 big calories. We want to go to little calories. So we're going to put big calories on the bottom, little calories on top. 1 big calorie is 1,000 little calories. So that would be 90 little calories. Okay, so this whole chapter discusses heat energy, and the energy transferred in different processes. So heat gets the symbol lowercase q. So this is heat, and it stands for quantity of heat. That's why it's a Q. And of course, it's measured in joules or in calories or kilojoules or something like that. Now, chemists like to be fancy, and so they're not just okay with just Q. For chemical reactions or processes, instead of just calling it heat or quantity of heat or using Q, they came up with a fancy name, which is enthalpy. And this is how you write it. You can pronounce it enthalpy or enthalpy. I've heard both. Both are okay. The symbol for enthalpy is delta H. Q and delta H, or heat and enthalpy, are kind of the same thing. They mean how much energy is transferred from hot to cold. They mean the same thing. Usually we use delta H if it's like a chemical process. Usually we use Q if we're talking more of a physical thing, like, you know, I have a cup of water that I'm heating. How much heat does it absorb? Versus I have a chemical reaction. What's the enthalpy of the reaction? Again, they mean the same thing. They're both the energy that is transferred in a process. It's just a fancy way of saying heat. So when we talk about enthalpy or heat energy or heat, they mean the same thing. When we use Q or delta H, they mean the same thing. Again, delta H is usually used for chemical reactions. Q is usually used for other processes. So heat or enthalpy is the flow of energy due to a difference in temperature. We said it always flows from hot to cold, from the faster moving particles, which are hot, to the slower moving particles, which are cold. And so we use Q or delta H. There is a difference between heat and temperature. So let's talk about that. Temperature is the measure of the motion of the particles. So the higher the temperature, that means the particles are moving fast. So temperature is kind of telling us how fast are the particles moving. Whereas heat is the flow of energy from hot to cold. There is a Eureka video. It's a cartoon video called Eureka, and it talks about the difference between heat and temperature. So it's on our Schoology page, so I would like you to watch that, and that's going to kind of help you understand the difference between heat versus temperature. So temperature has to do with the random motion of the particles, how fast the particles are moving. It's measured, its units are Celsius or Fahrenheit or Kelvin, versus heat is how much energy is transferred because you have a difference in temperature. Because some particles are moving faster than others, so you're going to transfer some energy from the fast-moving particles to the slow-moving particles. And heat is measured in joules or kilojoules or calories. So let's say you have a bucket of water at 310 Kelvin and a cup of water at 310 Kelvin. Compare the temperature and the heat that each can transfer. Let's say can transfer instead of contains. So they're both at the same temperature, so they're going to have obviously the same for the temperature. Since they're both water and the same temperature, they both have the same average speed of their particles. But the bucket of water can transfer more heat. So imagine this. I heat up some water and I put one drop on my hand versus I pour a whole cup of hot water on my hand. Which one's going to burn me more? Which one's going to transfer more heat to my hand? Well, the cup that's full of hot water compared to the one drop of hot water will give more energy to my hand and therefore burn me more. So I'd like you to watch that Eureka video. Have a great day, guys.